So, in this video we are going to learn how to use the Le Chatelier principle in a chemical equilibrium problem. But first, what Le Chatelier principle says. When a chemical system at equilibrium is disturbed, the system shifts in a direction that minimizes the disturbance. We can disturb a system in a chemical equilibrium in several different ways, including change in the concentration of the reactants or products, change in the volume or pressure, change in the temperature. We are going to see all these cases through examples, but in this video we are going to focus only in the change in the concentration. This example deals with change in the concentration. Before moving to the example, you have to keep in mind that changes in the concentration does not impact the equilibrium concentration. It is going to shift temporarily, and after that is going to reach again the equilibrium. So, keep in mind, change in the concentration does not change the equilibrium constant. So, some hydrogen and iodine are mixed at 300 degrees Celsius, constant temperature, in 1 liter container. When the equilibrium is established, the following concentrations are present. These are equilibrium concentrations: 0.49 molar, 0.08 molar, and 0.06 molar for iodine. If an additional 0.3 mole of hydrogen iodide is then added, what concentration will be present when the new equilibrium is established? First, as you can guess, we have to find the concentration for the hydrogen iodide. This may look like the acid, hydroiodic acid, but be careful because we are in the gaseous state here. That's why we call it hydrogen iodide. First, what we can do? We can find the equilibrium constant by the equilibrium concentrations given here. So let's find it. So let's find now the concentration for the hydrogen iodide added, the 0.3 moles. Keep in mind the volume of the container is 1 liter, so it's 0.3 molar hydrogen iodide. Now at this point we are going to build a table that is slightly different from the initial change equilibrium table. So let's build the table. So first row of the table, we are going to place the equilibrium concentrations that we have given by the exercise. At the second row, we are going to add the addition. Where we add, so here no, we add 0.3 molar hydrogen iodide. When we add 0.3 molar hydrogen iodide, after the addition, the system moves from the equilibrium to a new initial concentrations. Again, here is equilibrium plus addition. At this point, we don't know in which side is going to happen the change. From a critical point of view, we can understand that the equilibrium is going to shift to the left because we are in an equilibrium, we add a product, and of course equilibrium is going to shift to the left according to the Le Chatelier principle to minimize the disturbance. But there is another way that we can find for sure which side the equilibrium goes by calculating the reaction coefficient. I will link that video in the description, what is the reaction coefficient and how to use it. So, reaction coefficient is going to be the concentration for the reaction coefficient are the new initial concentrations. From the definition of the reaction coefficient, it doesn't matter at which point we are measuring the concentrations. We see that the reaction coefficient is 130, which is bigger than 50 that was the equilibrium constant, which tells us that the direction of the change is going to be toward reactants. So be careful when you place x's here because you have to take a look at the coefficients in the balanced equation. We have 2, 1, 1, which means minus 2x because you are consuming products, plus x forming reactant, plus x because it's 1 here, 1 here, minus 2 because it's 2 here, the reaction coefficient. So let's sum to find the new equilibrium concentrations. So now let's place these new equilibrium concentrations to the equilibrium constant and find the new equilibrium concentrations by solving for the x. You can see here that Q looks similar in expression with the equilibrium constant. The only difference is that the equilibrium constant deals only with the equilibrium concentrations. This is equal to 50, the value of the equilibrium constant. If you solve this kind of mathematical operation here, you're going to this point. You come to a quadratic equation. By solving this quadratic equation, you can find x2. As I mentioned in a previous video, that you have to select only one value for the x. Mathematically, they are both meaningful, but in terms of chemistry, is only the x1 because we cannot have negative concentrations. And let's place this x1 to the new equilibrium concentrations to find the new equilibrium concentration for our species. These are the new equilibrium concentrations. Thanks for watching, guys. See you in the next video. Peace.